to start the body. So let's go back to the first page. So today we started the concept of solid angle, and I hope this diagram making some sense to you as per the discussion.
Yes, sir.
And then we try to derive the solid angle for a spherical patch, and we got something like this.
Yes, sir.
And then we move on to the relation of the solid angle and the answer of the electric field to disk. And we saw something very interesting here. Then we try to derive a generalized formula for the solid angle, and we got this answer. And then we applied the same concept to for a disk form problem, and we got the same result but slightly in a different method. So this formula is not just for the flux is not just one way. So in fact, you can find the force between something like that also. So okay, we'll see a different method also. This is the two method, but eventually you will come to across something called the third method also, called the flux method. Anyway, so now there are two small concepts that we should be aware of, and that's called the uh, types of surface and concept of solid angle. Sorry, concept of area. So imagine so we have two types of surface. So if a surface is open, it can be flat, it can be curved, but the whole idea is it is open surface. So as long as the surface is open, the area vector will have no particular choice. You can choose as per your convenience. So if it is a flat surface, then you can choose it on either side. Okay,
Yes, sir.
because area vector must be perpendicular. But imagine if you have a surface which is curved surface. So it is open surface but a curved surface. So can we define the unique area vector here? Do we have the unique perpendicular?
Sir, as in like one common for like the entire patch.
Yeah. Yes.
So maybe we can draw like a surface that is like joining all the ends of this surface and a perpendicular to that.
So let's say you take a small a part of a bowl shape like this. So can we do this like one single normal for every point of the surface? Yes or no?
I don't know, sir.
Okay. This is bad. Okay, so what I'm trying to explain is, in case of flat surface, if you draw normal everywhere, all normal will be in the same direction. Yes or no?
Yes, sir.
So can we say we have a unique normal direction only?
Yes, sir.
But if you look at the curved surface, the normal, if you try to draw here, it is like this.
The direction perpendicular to the tangents drawn are different at different
Exactly.
places.
Correct. So we have infinite normal, isn't it?
Yes, sir.
Which simply means we cannot have a unique normal for curved surface.
Okay.
Yeah, of
Yes,
course,
sir.
it can be in the both direction, but the problem is we have infinite. And therefore, because we don't have the like one particular direction, so the whole idea is that in case of a curved open surface, we cannot define the area vector. We can define area vector of a part of it, which is the patch. So I may take a small patch here and I can define, or I might take here and then define. So instead of the whole surface, we can define the dA vector only. We cannot define a vector. But here we can define both dA and so whether it's a plane, if it is a planar surface, then the good thing is that you can apply, you can take a small patch or big patch, all will have same direction. So we have unique direction. But in case of curved surface, the big patch will not have a direction at all to be defined. So you can only define the elementary area vector. You cannot define the area vector.
Yes, sir.
So the big area is not possible. The small area is possible. Okay.
Okay, sir.
Now the flexibility is if it is the open surface, then we can draw the normal on either side. That is allowed. Okay.
Yes, sir.
What about the closed surface? So if we draw a closed surface, and closed surface is surface which captures some volume. So when we say a closed surface, it means it will capture some volume without any hole, like no gap.
So are you speaking something?
No, no, I was not. So in case of closed surface, we have internal area or internal volume. Now in case of open surface, something like that do not exist. So we don't have interior and exterior because it's open. So open means you don't have side. You don't have the priority. Okay.
Okay, sir.
Also, you should remember that when I say open surface, even if I draw like a feature, if I draw a surface like this with let's say balloon and imagine this is filled. but there's a mouth which is open. So what surface we can call interior or exterior? Sorry,
So when you say it's filled, what do you mean, sir?
I'm saying it's a balloon kind of shape. So one side is open to like the edge is not like covered or you can say closed. So this will belong to open surface or closed surface. That's the question.
Sir, open surface.
Correct. So every surface, even if you make a one small hole, it becomes open surface. So when I say closed surface, then it is a hypothetical imaginary closed surface that we are trying to create in our brain. So for any closed
Okay.
surface, the freedom to decide the area vector will be absent, and the only direction we can choose is the outer one. That's it. We cannot have the internal. I mean, we cannot draw this way. Area vector we will have. So we say that for closed surface, the area vector must be along the direction of outward normal.
All right, please.
Okay. Now the same rule will be applied if it is a flat surface. So imagine if you have a cuboid or cube kind of shape, then every surface will have its own area vector, right?
Yes, sir.
So how many area vector we need to completely define the cube, cuboid?
Sir, 6.
Very good. So let me make a confession. I have been teaching this topic for almost 14 years, but you are the one who has understood in the least effort. So for me, today lecture is the easiest one. Generally, I need to keep on shouting in the classroom to explain this to make them understand the topic. They simply don't digest what I'm saying. But I'm fortunate that you're getting it really easy.
Thank you, sir.
God bless you. Keep on doing like this. Okay.
Yes,
So
sir.
now, if it is a cuboid, then we have six surfaces, and you can see the left surface will have the left area vector, but the right will have the right. So they don't have the same area vector. They are opposite in direction. So this is how you can see the area vector. Okay.
Yes, sir.
And now you can go for the curved surface. So the same rule will be followed for curved surface. It must be curved, right?
Yes, sir.
That's the only rule. So if I draw a cylinder, let's say this example. Okay. So because we have a cylindrical surface, so if I look at the top surface, then this is the area vector, and if I look at the bottom surface, this is the area vector, correct?
Yes, sir.
So we may have the unique area vector for the top and the bottom. The reason being they are flat surfaces or plane surfaces. Okay.
Yes, sir.
But when we talk about the part which is like the lateral surface, then we cannot define the area vector for the entire lateral surface, but we can take a patch, and the patch is really small, as good as a point, and the patch will have the area vector in the direction perpendicular to the point taken, or you can say the tangent plane at that point will be like this. So that is the rule all about closed surface and open surface. So closed surface will have the area vector in the direction of outward normal. For open surface, it can be in either side. Also, we need to understand that if you are interested in the area vector, please think of whether it's a plane surface or curved surface. And if it is a plane surface, then you can uniquely define. But if it is curved surface, then you have to go back to the elementary area concept. And from there on, you can solve the question. Okay.
Okay, sir.
So what is the next concept? So this is the concept of area vector. The area vector and types of surface. Good. So next we can go. This page I have to leave. What I can do with this page? I have so much space left. Leave it. Next page. Hmm. Yeah, I can write something here.
So your voice has gone a bit low.
Yeah, I'm saying it on a feeble voice. Now it's audible.
Yes, sir.
Okay. So that's only one example here. Coming to this page. Next. Mhm. So we can go to the concept of so before we enter the concept of Gauss law or the uh, flux, we need to understand the concept of electric field lines and what are these lines and why we are learning today about these lines. So electric field lines are also known as okay. So
Okay, sir.
5 minutes break. Okay.
Oh, yes, sir.
Okay, I'm back. Are you there?
So, yes, sir. So you can just come back in a minute, sir.
Ah, yeah, sure, sure.
Uh,
Are you there?
so yes, sir, just now came back, sir.
Okay. So now this is a concept that we just need to understand. It's pretty easy concept, but the whole purpose of introducing this concept is to give you a visual picture of certain electrostatic phenomena. So you can understand that this is just like an animation, which is not real, but it helps us in actually creating some intuition in the brain. Okay, so these are
Okay.
basically graphs. You can think as a graph, a three-dimensional graph. We are trying to plot on a two-dimensional blackboard. So always remember that I may be drawing it two-dimensionally because of the obvious reason, but these things are three-dimensional in nature. Okay,
Yes, sir.
so the whole idea is what are these EFL electric field lines? So we say that these are so these are imaginary lines of this domain. I got lost in it.
So
These are
is
imaginary lines which are used for giving visual description of electrostatic phenomena. So that's the whole idea. Okay.
okay.
And because this is just an idea, so there must be some underlying assumption because every idea will have some assumption. So what are those assumptions? The first assumption is from isolated okay. So if we have a positive point charge, then the electric field lines will emanate in the radially outward direction. Okay, and this will be three dimension, not two dimension. So it's not like a in a plane. It will be happening in all direction. Okay.
Yes, sir.
Similarly, due to isolated negative point charge point charge So that is the two most important concept of electric field lines, that from a positive point like charge, it will radiate outward, and for isolated and negative point charge, it will terminate inward. So the role of plus charge is to release and the negative is to terminate. So the question is how much they will release and how much they will terminate. It means there should be some sort of measurement about either emanation or termination. There should be some measurement, isn't it?
Yes.
So due to positive, you can do in all directions. So that is the only difference, uh, the beginning and the end. So if it is isolated, it means we are assuming that there is no uh, charge present in their proximity, or even if it is present, it is not influencing in any particular way. So this is the lines of force will look like. So these are like spherical emission and termination, spherically. Okay.
Yes,
So
sir.
the lines of force leaving the point charge will be in how much angle? So they leave at angle of 4 pi. Steer radian. Understood?
Sir, like all the directions.
Yeah, that's a spherical direction. So that's why it's a three-dimensional pattern, not a two-dimensional. And similarly here, this is three-dimensional. So it will terminate with this steer radian angle. Okay. So the question
Yes,
is how much it will release or terminate. So will it be same for all charge or will it be different for all charge? That's the question. So logically speaking, it should not be same for all charge. Otherwise, no matter how much charge you choose, all will give the same electric field, isn't it?
yes, sir.
So there should be some relation. And the metric that we use to measure the amount of emission or termination in relative to charges is given by the value. We say that number of EFL. oh, So relative number of electric field lines either emanating from positive charge or terminating on negative charge. So relative number of EFL either emanating from positive charge or terminating on negative charge is proportional to so what we can say that every charge will actually emanate infinite number of field lines everyone. But if everyone is emanating infinite, then how to compare which infinity is bigger and which infinity is smaller? Okay. So let's say if you talk about the number of hair strand on a human head, then definitely it is uncountable for everyone, isn't it?
Yes, sir.
So we cannot count the number of hair strand on everyone's head, isn't it?
Yes,
But
sir.
still we make a comment that okay, your hair is like denser in look and not so denser in look. So someone is having a more uh, fulfilled, you can say, head, and someone may have the less fulfilled. So that's like a relative comparison, but both are uncountable, isn't it?
Yes, sir.
So generally, the younger generation will have the more hair, I mean, hair count, but as we grow old, we lose some hair strand. So we get some bald part or patches on our head. So in both cases, they are uncountable, isn't it?
Yes, sir.
But still, we can compare that. Okay, your is more, your is less. So how to make that comparison? So we say that it is proportional to charge. So the relative amount of lines of force coming will be proportional charge. So if I choose a symbol phi to represent the number, and the same phi we are going to call later on as flux. So let's keep it simple. So number of EFL is proportional to magnitude of charge. So we can write equals to uh, we have to multiply by some constant. So we write as epsilon naught. So this is the relative field density measurement. So measurement of a relative field density, which means if we have a charge q, then the metric of measurement of number of field lines you can call q by epsilon naught. Okay.
Yes, sir.
So if the number of this is the value, then the point charge will emanate this much field in how much angle? So this will radiate through the 4 pi solid angle, isn't it?
So this is like the total
Line.
number of.
Correct,
Oh,
correct. Total number of field lines, correct.
okay.
So let's say if I am only interested in knowing the field lines, just a minute.
So I speaking something.
Yeah, sorry. So now let's say I'm not looking for the total angle. I mean the total field lines. I'm just let me draw first of all a straight line, and then I will draw something. So I want to know how many lines will only go through this angle. So I want, let's say this is theta. So out of the whole, see this will radiate from how much angle? 4 pi.
Yes, sir.
So how much will go through the omega part? Like what is the lines
Sir, omega
trapped?
by 4 pi into q by e naught.
Exactly.
So,
Correct. So the number of EFL through omega solid angle will be equals to the fraction into total, right?
yes, sir.
And now because it's a conical angle, so omega we can write as, if you remember the derivation,
Yes, sir.
so we generally every time if I have to write this literature, it's not good. So I will choose a symbol phi for the symbol. And in some context, this may become flux, so that's good symbol to use. And to represent the electric flux, we call phi e. So this becomes the answer as q by 2 epsilon naught into 1 minus cos theta. Okay.
Okay, sir.
So now you can understand the flux or the number of field lines, the count of the field lines through the angle theta of a cone. Theta is the angle of semi-vertical angle of a cone. You can write easily by the formula q by 2 epsilon naught 1 minus cos theta. Now, this is the most important formula for the further discussion. The most. Very, 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 very important.
Okay, sir.
So just remember.
So,
Yeah,
sir, in this q by e naught, it's like the relative number of field lines
yeah,
that we are considering.
correct, correct. So the number is infinite. In count wise, if you talk about the count, it's uncountable. But if you talk about the count density, like which one is more denser, then we can say it is proportional to charge Q. So you can always keep this in mind. This is like a count itself.
Okay, sir.
So let's say we have two guys, one young, other is old, and if you take a same patch on the head, the number of hair stand on the younger will be more,
Yes, sir.
and slightly older will be like this.
Yes, sir.
So although we have taken the same area, is the count same? No.
No, sir.
So if the charge is assumed to be Q here and Q dash here, then the count to compare, we can say this is the count for this. This is, so if Q is more than Q dash, then the count will be also more. So this is how we compare relatively. That's it. Understood?
Yes, sir.
So we'll see some use to understand what we are trying to do. So now we can come to the concept of plus minus charge. So if we have a plus charge which is isolated and or minus which is isolated, then plus will emanate and minus will terminate explicitly, right? But
Yes,
the question is, what about if we have the plus charge kept in the vicinity of minus charge? Then can we say the same? The answer is no, because now they will affect each other. But nevertheless, if I try to draw the charge as a dot, if you think of the plus and minus as a dot, and if you draw a tiny sphere around the dot, then the reality is the electric field will be actually spherical around the dot. And it will emanate like this. And it will terminate radially. That's correct.
yes, sir.
So very close to the charge, the emanation and termination will be spherical again. That is true. Okay.
Yes, sir.
But if you try to go away from it, then something else will happen. And what will happen is, I'm drawing here. So the moment you go away from it, it will actually start bending towards the negative. Because what will leave the plus, the minus will try to terminate. So if it will leave like this, it will terminate like this. So you may leave like this, but eventually will turn and so oh, so if it will leave like this, so it will go infinity and then come like this. So everything leaving the surface will come back by either. So if something will leave like this, will go, and then eventually come like this. So it will leave like this. Will because of attraction, it will try to go back and will come like this. So you can see that everything leaving the positive is eventually coming the negative and terminating. Okay.
Yes, sir.
So graphically, how many lines of force or how many field lines are leaving the plus? Can you count?
There
1,
are 1,
2,
2,
3,
3.
4, 5, 6, 7, 8.
Yes, sir.
And how many coming back to the negative? Can you count?
Sir, 8.
Exactly. Now you can draw 16, 16, 20, 20, 1,000, 1,000, million, million, but we have a limitation. So the whole idea is that this is the graph actually. This is not a count. This is not a reality. This is just a graph. And I have just chosen few graphs, not all graphs. Okay.
Yes, sir.
So what I am saying that if the number of field lines leaving the plus, which I'm drawing here, and if the number of lines which is coming to minus, if they are equal in count, it means the charges are equal in magnitude. That is the whole idea. So if I call this as plus q, this must be minus q. Understood?
If it's all the field lines that terminates them.
Yes. So if whatever is leaving is terminating, it means they are equal in magnitude.
So that means like if there is extra number of field lines that does not come from plus q,
Yeah,
then
yeah.
minus has a greater magnitude.
Correct, correct.
Okay, sir.
So imagine if I draw something like a big positive charge, but a weak negative charge. Then lines of force will have very interesting shape. It looks really nice. So it will begin from plus, will terminate. Now it will. Oh, okay, now one question. Now the emanation and the termination occurs by equal value. So if 10 will emanate, then the lower will decide the capacity. So if I say the number of field lines which will come out of this much, and the number which can terminate is this much, and if this is bigger, so the smaller will decide the termination or emanation, only smaller. Okay. Now what does it mean? The small will only terminate what you are capable of. I mean, sorry, only terminate what it is capable of. So if I draw two angles close to the charge, and if I say this angle is same and this angle is same, then which solid angle will contain more field lines? Tell me.
Sir, the plus Q.
The capital, correct?
Yes, sir.
So to make them equal, which angle I must decrease?
Sir, the plus Q.
Very good. So we can understand one thing, that the lines of force which will actually terminate, so the extreme angle up to which it can terminate will have value. If I call alpha, then it will terminate something like this at angle beta. You can understand why.
Yes, sir.
Because beta should be bigger than alpha, isn't it?
Yes, sir.
Otherwise, what will happen?
Sir, the smaller Q won't have enough capacity to terminate all those field lines that the plus Q is emanating.
Correct. Very good. Excellent. So there is always a relationship between, and this is the most challenging concept. So if I draw a line, tangent line here, and if I draw a tangent line here, the bigger angle will always correspond to the smaller charge, isn't it?
Yes, sir.
The bigger angle of emanation or termination will lead to the small charge, isn't it?
Yes, sir.
So if I want to establish a relation between alpha and beta, then can we say the flux of the flux through the alpha, the flux through the alpha angle must be equals to the flux through the beta angle for the small charge,
Yes, sir.
and we know the formula how to write.
Sir, I have one doubt, sir.
Yeah.
Sir, I don't understand like how plus Q like adjusting its like the field line path, like how will it help in
Okay, just
getting the minus Q?
yeah, yeah. So okay, before we solve this question, let's try to understand the field lines first. Okay. That's a good question. What you're trying to understand. Okay. So have you seen a jellyfish?
So a jellyfish? Yes, sir.
Yeah.
Yes, sir.
In real or
Sir,
only
in real, sir.
very good. In aquarium or in the real pond or ocean?
Sir, in aquarium only, sir.
Okay. So luckily I have seen the real, like face to face.
Wow.
Yeah. So somewhere in the Sri Lanka is one. anyway, and it was very dangerous. So the instructor told me don't touch, else you will get the itching. So they are poisonous. Mostly jellyfish are poisonous. So you cannot touch everywhere. You can touch at some particular point to be safe.
Yes, sir.
So imagine the plus is emanating, and I'm assuming the plus is bigger than the minus. And why suddenly I'm talking about the jellyfish? You will come to know.
I don't know, sir.
Yeah, you don't know, but you will come to know now. So the lines of force will be like this.
Yes, sir.
This is the lines of force terminating, and some more. Some more. Let's say something here. Now, let's say this is the capacity. Is not anything beyond that. So what will leave here? We will terminate here. Now beyond that, this will go something like this. Let's change the color actually. You can see they're not terminated. So these are some fancy lines of force, right?
Yes, sir.
And now you can understand why I was talking about jellyfish. It looks like jellyfish. No?
Yes, sir.
So the field lines will behave quite differently if the charges are having different magnitude. So I chose the plus to be bigger and minus to be smaller. Now, graphically, the rule is the counting will give you the relative value. So can you count the plus and minus? So how many are coming out of from plus? Just count.
Sir, for plus, it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
14.
So
14.
14, yes, sir.
So the plus q is leaving some, minus q is terminating. And how many are ending here terminating? Can you count?
So 6, sir.
So the ratio is 14:6. The charge ratio. This is how we interpret. Understood?
Yes, sir.
Because the graphical representation must be in proportion. So yeah, if I know that the first charge is twice the second charge, I must make the ratio 1:2 or 2:1, depending. But if they give you graph already and tell you to predict the ratio, you can say the answer is 7/3. Understood?
Yes, sir.
Okay. So which charge is smaller? The minus q, right?
Yes, sir.
So the electric field will be zero near which region?
Sir,
Right of minus q plus q, left of minus q plus q, between them.
right.
Hmm?
Sir, it will be right of minus q, sir.
Very good. So if you remember, this is the same question we have solved already. So if you have a plus q and minus q, so the field is zero always near the weaker charge, like outside and near the. So they have opposite sign. So when charge is opposite the field will be 0 either on the right or left, not in middle. And you can also see something interesting. The field lines are opposite here, right? So
Yes,
one
sir.
is going right and other is going left. So the chance of cancelling is there actually. Okay.
Yes, sir.
So that is also logical in many ways that the electric field lines will try to cancel their effect on the right of field. So it will be 0 somewhere on the right of this. And this was the JE Advanced 2010 question. Simple. MCQ.
Sir, what was the question, sir?
The question was find this ratio and this where the field will be 0, right of that, left of that, and so on.
Oh, by using like the number of field lines
Yeah,
emanating at it.
correct, correct. So now you can say that you can see something. The last lines of force which is terminating having some angle, and the
Yes, sir.
last which is coming here is beta angle, and the
Yes.
rest is not part of the journey. So I would like to know the alpha and beta relation. So what I can say that the total field lines in this solid angle and here must be equal,
Yes, sir.
and that is what I was trying to solve here.
Okay, sir.
So the count of field lines coming from the alpha angle, like this solid angle, and the one which is terminating here, they must be equal.
Yes, sir.
So we can derive a very nice formula, and that is so now we can say the flux. Okay, the better way of writing will be the flux through the omega 1 must be same as flux through the
Yes,
omega
sir.
2. So how to write the flux in terms of charge? So can we
Sir,
write q by 2 epsilon naught 1 minus cos alpha,
yes, sir.
and here you can write as q by 2 epsilon 1 minus cos beta.
Yes, sir.
So we can write q by q equals to hmm, like this.
Yes, sir.
Okay.
Yes, sir.
So this is a, relation, and this is a question from Russian Olympiad. It's a very old question, but that's a very relevant question. Okay. So this is the relation between the plus and minus charge. Now we can do something. So some property we need to remember. 2 EFL cannot. Okay, no. This is very famous and known to everyone. The first concept is electric field lines always represent net electric. So electric field lines always represent net electric. Okay.
Okay, sir. Sir, net electric field at a point
Yeah.
or
Yeah,
at a
every
region?
at every point in the region. In the region surrounding the charge. Okay.
Okay, sir.
So the second concept is the tangent drawn to the EFL in the direction of its flow. Flow means plus to minus. Okay. So direction of flow gives the direction of electric field. Okay.
So,
Yes. Audible?
yes, sir. Sir,
So tell me.
sir, like the number of electric field lines passing through a certain region gives like the strength at that particular region, right? So, like the field
No, no,
strength.
no, no, no. It's like the proximity of the field lines will be the same. Like if we see really close lines, closely packed, then we say
Yes.
strong field. And if they're loosely packed, we say weak field. That's it.
Okay, sir.
But
Sir,
at
that means yes,
yeah,
sir.
from one particular point, only one line will pass.
Yes, sir. Like that was pretty much my doubt, sir. Like
Yeah.
there's a charge, and at a certain distance, at a particular point, if they ask us to, I mean, like if a field needs to be calculated.
Hmm.
So by electric field lines, how do we understand this, sir?
So at a point, you can draw field lines due to the plus charge like this.
Yes, sir.
So you can clearly see as you go away, the gap will grow.
Yes, sir.
So what is the meaning of gap? They are getting divergent, so it means the field is becoming weaker and weaker and weaker.
Okay, sir.
So if you go away, the divergence will only grow now.
Yes, sir.
That's a simple reason the field becomes weaker. We cannot find the value. We can only find the relative value, the relative strength. We cannot talk about the answer, the numerical value. Understood?
Okay. Yes, sir. Sir,
So,
so even if we try to calculate the field at a point, we
hmm,
are seeing the proximity of the lines which are
yeah,
around it.
correct, correct. So let's say if I draw something like this, we have already drawn for the previous case.
Yes, sir.
And you can clearly see that here we have very close proximity. So very
Yes, sir.
strong electric field, very powerful electric field, very, very powerful. And if you come really close, it is like infinitely dense.
Yes, sir.
So this is the strongest field. Now it will become weaker, 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 weaker. But after reaching the midpoint, it is the weakest because the gap is maximum. But
Yes, sir.
again, it is converging. So again, it will become stronger, 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 and then powerful, the most powerful. Understood?
Yes, sir.
So that is the whole idea, that the separation between the EFL which we draw is like a proportional to the strength of the field, like inversely proportional to the strength of the field. So more the separation, weaker is the field. Okay.
Okay, sir.
So the strength is inversely proportional to gap between the lines. All right.
Yes, sir.
All right. So the tangent drawn to the EFL. So let's say I'm looking for a field lines, electric field direction at this point. Then this will be along the flow and tangents. This something like this.
Yes, sir.
So if I want to know at this point, it will be like this. Just do a tangent, and that's it. And
Okay, sir.
every point will have a unique tangent, isn't it?
Yes, sir.
Now that comes to the conclusion that 2 EFL cannot intersect each other. Cannot. Two electric fields cannot intersect each other. Why?
So, because both the origin and the direction cannot be like same.
Yeah. Let's say if they intersect, what will happen? We can draw two tangents.
Yes, sir.
But if I draw two tangents, it means we have two field direction at one point. And this is not the property of field lines. We cannot have the two direction at one point, isn't it?
Yes, sir.
So if I throw a ball, I cannot think that a ball in at certain point of the sky will move in two directions at the same time,
Yes, sir.
unless it is not broken into two parts.
Yes, sir.
So at one point we only expect one line. So intersection will lead to the absurdity. Like at one point we have two field directions, and because this is not going to be possible, so we say this is not possible. So they cannot intersect because if they do so, then you can have two direction of electric field lines at one point, which is physically absurd. And that's simple answer. Okay. Also, you need to remember the electric field lines when we draw for all charges taken into consideration. We don't draw for one charge particularly. So you can see the positive will have a different behavior, negative will have different behavior, but if they come together, you can see this is some different behavior. So we can understand clearly that the field lines represent the net field throughout the region, not the field of individual charge. Understood?
Yes, sir.
So if you try to
So,
find the resultant field at a particular point, just think of the net field at that point and you're done. Okay.
okay, sir.
So if I draw three charges at the vertex of triangle, although it doesn't look like, but assume it's a equilateral triangle. So if I want to draw the electric field lines, how we can do it?
Sir, they go straight, they go really upward, but then I guess they will like, um, so they'll move away from when like two electric field lines come closer.
First of all, try to think this way. First question: electric field lines represent the net field. Okay.
Yes, sir.
So at which point the net field is going to be zero before we draw anything? Center.
Sir, at the center.
Very good. Also, what about the field at the center of the edge? Every edge.
Sir, only due to that, the one opposite to the word,
Right.
like the vertex will be going.
It means at this point the field must be like this.
Yes, sir.
At this point, the field must be like this. At this point, field must be like this, isn't it?
Yes, sir.
So the whole idea is the rest we can only guess. So I mean, of course, we cannot draw the exact field lines, but we can draw the rough nature of field lines, and we can say that no lines of force should come at the center, because if they come, they will cut, which is not possible. So the field lines will be coming here, but leaving like this. They turn.
Yes, sir.
They turn like this. So again, don't try to think of it that these are exact diagrams. These are like a rough approximation of the situation.
Yes, sir.
And rest you can just think. So, okay, what is the net field at this point? So the net field will be like this.
Yes, sir. So these field lines are due to the same charges itself.
Yeah. And of course, the other two will also add. So now we can think that the field lines are like this. Something like this. Okay.
Yes, sir.
So this is the direction of electric field lines, and but later on we come to know that graphically we have known or seen that the net field is zero even at a point somewhere here, which I cannot draw. Sorry, not this. Here, somewhere here. So apart from center, there are few other places where this is also true, but that is mathematically challenging to solve. So we can just remember that center is zero for sure, but we have three more points where it is also zero. And to prove that, I can give you some intuition. So, so imagine we have just two charges, plus q and plus q. So the electric field at the center is how much? 0.
Yes, sir.
And at infinity it is also 0, isn't it? If you remember. So if you plot the graph of E versus X, we know the field will be 0, will start from 0, will become maximum, and then we start decay like this. Correct?
Yes, sir.
But we also have the third charge somewhere, let's say the third charge is somewhere here. And because the third charge is here, if you try to draw the field lines for this charge on the left side, so it will be infinity, because at close to any charge, the field is always infinite.
Yes, sir.
But as you go away, it will decrease.
Yes, sir. Sir, the blue is for
The third charge,
like
yeah.
when the third charge is there.
Yeah. We're doing separate. So it is something like this. I mean, difficult to do, but you can imagine. And what you can realize that there are 2 points of intersection, not one. Understood? So we have 2 points of intersection, as you can see. And that is how we come to conclusion that it is not just a centroid, but we have 2 particular points where on the same line where the field will be 0, because the field directions are opposite, right?
Yes, sir.
And you can see the magnitude cycle. Okay, so this is actually derived. We can solve this graphically in a like using 3D. I mean, using the some graphing calculator like GeoGebra, and we do get the answer.
Okay, sir.
Okay,
Yes, sir.
so this is the proof that and so this is true for every line. So you can see we have 2 points on a line, but we have 3 such points, right?
Yes, sir.
And this is true for every line. So we have in total 6. Sorry, 2 to 4 to 6. Yeah, we have total 6 pair, but out of 6 pair, all 3 will coincide at one point, so become 4. So 3 distinct and 1 common, isn't it? So you can see 1, 2, 3, 4, 5, 6. You can see this is collection of 3 points. So
Yes,
for
sir.
every configuration, 1 is the common point, and then we have 1 distinct point. So total number of what we call null points in a triangle is 4. Okay.
Sir, I don't understand the logic.
Okay. So how many? See, for this 3 charge, how many points we got?
Sir,
Two.
the blue is like the net field on the axis when the third,
Blue is the field of the discharge on third charge.
it's only the field of the third
Yeah,
charge
yeah,
and not like the net
No,
field
no,
that's
no,
measured.
no, 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 no. This is not the field line. This is the electric field graph.
On the axis.
Yeah, this is the numerical value. E versus X.
Okay, sir.
So value
So,
will be 0, will increase, will become again 0 at infinity.
Yes, sir.
Similarly, if I choose these two lines and this triangle, I can draw a similar graph on this line. So these two will create a field like this: 0 maxima and the minima,
Yes, sir.
and this will create a field like this,
Yes, sir.
and so we get again two parent points on this line,
Yes, sir.
and then again same for the this 2 point and this line. So again 2 points. So two, like one common and then one here. So two, two, and two. So there are 4 points, right?
Understood, sir.
Understood?
Yes, sir.
So I just demonstrated for one pair of points and the third point. So you can do it for the any. I chose 1, 2, and 3. This is due to 3, and sorry, this is due to 3, but this is due to 1 plus 2. Understood? You
Yes,
can
sir.
also do it for the 1 plus 3 and 2 plus 3, and then 2 and then 1 separate.
Okay, sir.
So every pair will give you 2 points. But out of 2 points, one will be distinct, one will be common.
Yes, sir.
So eventually the total will be how much? 4.
4.
Does this make sense to you?
Yes, sir.
Very good. So I think we should stop here for today. And on Sunday, I'll complete this part. And after completing this part, the Gauss law is pretty much easy. So don't worry about the Gauss law. So that will finish. And after Sunday, we can start the. So on Tuesday, I think which is 27th, you won't have any lecture. That I will schedule some other day.
Sir, our regular lectures are on Monday and Thursdays.
Then it's fine. Then it's fine. So Monday you will have lecture. So you can complete on Monday and then on Thursday. And then
Yes,
again on Friday or Saturday we'll try to pick one more.
sir, on Sundays also, this Sunday we are having lecture, right, sir?
Yeah. This Sunday
Okay, sir.
timing I will communicate that day only because right now even I don't know how the schedule is. So for Sunday I will let you know. Okay.
Okay, sir.
Okay. So let's end the lecture.
Sir.
Yeah.
Sir, the Anurag Mishra book that you told to buy, sir. So one of the links it had only second-hand books, sir.
I think the new book should be there.
Sir, I tried searching for it, but then like.
No. So if I find some link, I'll share. Otherwise, I'll share the soft copy of the book. You can study from soft copy also.
Sir, it doesn't give like the feel well problem solving.
Yes, same for me. So I'll try to find the book link of the book, and hopefully you should get it from Amazon. Okay.
Okay, sir. Otherwise, some nearby bookstore like that can courier the books.
Yeah, they can. I mean, I'll try to find them. I mean, normally even I don't go outside, but if I find in bookstore, I'll let you know, and then I will courier from here. Not an issue. Okay.
Okay, sir. Yes, sir. Thank you, sir.
You want the entire series or some particular book?
Sir, you gave the links for optics, electromagnetism, and to mechanics and thermodynamics, sir.
Yeah, right. So that's
so both the electromagnetism and the mechanics and heat and thermodynamics, all of them were second hand.
And that's not an issue. Even if you're getting second hand, that's good. But I'll try to find the first hand and we'll let you know. Okay.
Okay, sir. Thank you, sir. Bye, sir.